Welcome back to Rust coding challenges. Today a classic. Given a linked list, does it have a cycle, a node whose next pointer loops back into the list, so walking it never ends? The obvious way is to remember every node you've seen, but that costs extra memory. There's a beautiful trick that needs none. Two runners, one twice as fast as the other. It's called Floyd's Tortoise Hare, and by the end of this video you'll know exactly why it works. And because this is Rust, we'll also meet a fun twist. The borrow checker won't even let you build a looping list the normal way. Let's go. Here's the setup. A linked list is a chain of nodes, each pointing to the next, ending at nothing. A cycle means somewhere a node points back to an earlier one, so the chain has a loop, and if you just walk it looking for the end, you never find it, you go round and round forever. Our job: decide whether a list has a cycle. The easy solution takes extra memory proportional to the list. The elegant one, Floyd's, uses a constant amount, just 2 pointers, no matter how big the list gets. Here's why two runners work. Put a slow runner, the tortoise, that steps one node at a time, and a fast runner, the hare, that steps two. On a straight list with no loop, the hare simply reaches the end and falls off, and we answer no. But on a list with a cycle, both runners get trapped going around the loop, and because the hare gains one step on the tortoise every move, it slowly catches up from behind, and eventually they land on the exact same node. If the two ever meet, there's a cycle. That's the whole idea, and it needs only those 2 pointers. Let's build it in Rust. First, a small twist worth knowing. In Rust, the usual heap allocated list, a box pointing to a box, literally cannot form a cycle, because each node has exactly one owner, and a loop would need 2 things owning the same node. The borrow checker forbids it. So we represent the list as nodes in a vector, where next is an index instead of a pointer. An index can point anywhere, including backward, which is exactly how we'll build a loop safely. Here's the skeleton. The node type and 2 empty functions, the naive one and Floyd's. First, the naive version, so we have something to compare against. We keep a hash set of every node index we've visited. We walk the list, and at each node we try to insert its index. Insert returns false if the index was already in the set, and that means we've been here before. So there's a cycle, return true. If we walk right off the end into nothing, there's no cycle, return false. Correct and simple, but it stores up to n indices. That's the on extra space we want to beat. No Floyd's. 2 pointers, slow and fast, both starting at the head. Each loop, the hare moves 2 steps, and crucially, if either of those 2 steps walks off the end, there's no cycle and we return false. The tortoise moves 1 step, then we check. Are they on the same node? If they are, the hare has lapped the tortoise inside the loop, so there's a cycle, return true. No hash set, no extra memory, just the 2 pointers walking until they either fall off the end or collide. Let's run it on 2 lists, one with a cycle, 4 nodes where the last points back to the second, and one plain list that just ends. And there it is. For the cyclic list, both methods agree. True. For the plain list, both say false. Same answers from the hash set and from Floyd's, but Floyd's got there using a constant 2 pointers instead of a whole set. On a list of 1,000,000 nodes, that's the difference between 1,000,000 units of extra memory and, well, 2. The reason it always works. Once both runners are inside the loop, the hare gains exactly 1 step on the tortoise every single move. So the gap between them shrinks by 1 each time, and a shrinking whole number must eventually hit 0. They meet. It can never skip past, because closing a gap of 1 at a time can't jump over the target. And if there's no loop at all, the faster hare just reaches the end first and we stop. Linear time, constant space. That's why this trick shows up everywhere. From cycle detection to finding where a loop begins. Quick recap. The naive way remembers every node in a hash set, correct, but on memory. Floyd's Tortoise Hare uses 2 pointers, one moving twice as fast, and they meet if and only if there's a cycle, all in constant space. And the Rust specific lesson: an owned box-based list can't even represent a cycle, so when you need one, reach for indices into a vector or reference counting instead of plain boxes. A quick note, breaking these algorithms down in Rust line by line takes real work. If it helps you, the wallets are on screen and there's a Ko-fi link below. Every tip funds the next one. Thank you. That's cycle detection with Floyd's Tortoise and Hare, 2 pointers, constant memory, and a neat lesson about how Rust's ownership shapes the data structures you reach for. Subscribe so you don't miss the next challenge. Tell me in the comments which problem to break down next, and I'll see you there.